Look, every time you scroll through your phone, something absolutely miraculous is happening right under your fingertip. You touch the glass, just gently place your finger on it, and the phone knows. It knows exactly where you touched. It knows when you're swiping. It knows when you're tapping. But here's the thing that should blow your mind. You never actually touch anything, not really, not in the way you think you do. Your finger and that screen, they never make contact at the atomic level. There's always a gap, always. And yet, somehow, the screen detects you from across that impossible distance. It's detecting something invisible, something that reaches out from your body like a ghost. And the phone is reading that ghost. This isn't magic. This is quantum mechanics and electromagnetism dancing together in the most elegant way imaginable. Let me tell you what's really happening when you touch your phone screen. And I promise you, by the time we're done here, you'll never look at that little glass rectangle the same way again. The first thing you need to understand is that your phone screen isn't just glass. It can't be just glass. Glass is an insulator. It doesn't conduct electricity. So how does electricity get involved at all? Here's where it gets interesting. Coated on top of that glass, invisible to your eye, is an extraordinarily thin layer of something called indium tin oxide. We call it ITO for short. This stuff is maybe 300 nanometers thick. That's 300 billionths of a meter. You could stack 3,000 of these layers, and they'd still be thinner than a human hair. Now, ITO is special, really special. It does something that seems impossible. It conducts electricity and lets light through. Think about that for a second. Most things that conduct electricity are opaque. Copper wire, you can't see through it. Aluminum foil blocks light completely. But ITO, it's transparent. You can see right through it, while billions and billions of electrons are flowing through it every second. It's an N-type semiconductor with so many free electrons that it behaves almost like a metal. But its crystal structure is arranged in such a way that photons of visible light can pass right through without being absorbed. As Feynman explained in his lectures on electromagnetism, conductivity is all about free electrons, electrons that aren't tightly bound to atoms, electrons that can move. In ITO, tin atoms donate extra electrons to the crystal lattice of indium oxide, and these electrons are free to wander. They're like a gas of charged particles, ready to respond to electric fields. But the ITO layer isn't just one big sheet. No, it's been divided up into a grid, a fine mesh of horizontal and vertical lines. Imagine a checkerboard, but with thousands of squares. Each intersection in this grid is a sensor. When engineers design a modern smartphone screen, they're creating something like 10,000 or 20,000 of these intersection points. Each one can be measured independently. This is how the phone knows not just that you touched it, but where you touched it. Now here's where it gets really beautiful. The screen creates electric fields constantly. These fields are produced by sending alternating current through the grid, AC voltage, oscillating maybe at 100 kilohertz or more. Each line in the grid is generating its own electric field, spreading out from the surface of the screen into the space above it. These fields are reaching out into the air, into the space where your finger is about to appear. And your finger is a conductor. Not a great conductor like copper, but a conductor nonetheless. Why? Because you're mostly water, about 60% water, in fact. And that water isn't pure, it's filled with ions. Sodium ions, potassium ions, chloride ions, all dissolved in the water inside your cells and in the spaces between your cells. These ions can move. When an electric field pushes on them, they drift, they flow. That's what makes you conductive. That's what makes you real to the electric fields coming from your phone screen. Let's zoom in now. Really zoom in. When you bring your finger close to the screen, and I mean close, within a few millimeters, something extraordinary happens. Your finger becomes part of a capacitor. You know what a capacitor is? It's two conductors separated by an insulator. One conductor is the ITO grid on the screen. The other conductor is your finger. And the insulator between them, that's air. That's the gap that never quite closes even when you think you're touching the glass. Here's what Feynman would want you to understand. A capacitor stores electric field. The field lines start on one conductor, cross the gap, and end on the other conductor. The amount of field that can be stored, the capacitance, depends on the area of the conductors, the distance between them, and the properties of the insulator in between. When your finger approaches the screen, you're changing the geometry of the capacitor. You're creating a new path for the electric field. Some of the field lines that were spreading out into space now terminate on your finger instead. This changes the capacitance at that point on the grid. The change is tiny. We're talking picofarads, trillionths of a farad, but it's measurable. The electronics inside your phone are constantly monitoring the capacitance at every intersection point in the grid. They're looking for changes. When the capacitance suddenly increases at a particular location, the phone knows something conductive just appeared there. But let's go deeper. Let's understand what's really happening at the atomic level, because this is where the true physics lives. When the screen generates its AC electric field, what's actually happening? Well, the voltage on the ITO grid is oscillating, going positive, then negative, then positive again, hundreds of thousands of times per second. This oscillating voltage pushes and pulls on the free electrons in the ETO. The electrons jiggle back and forth. They don't go anywhere on average, but they're in constant motion. And this motion creates a changing electric field that extends beyond the screen surface. Now, electric fields are real. They're not just mathematical abstractions. An electric field is a condition of space. It's a property of the vacuum itself. When an electric field exists at a point in space, it means that if you put a charged particle there, that particle will feel a force. The field is the mediator of the force. This is one of the great insights of 19th century physics, refined and made quantum mechanical in the 20th century. When your finger enters this field, the field interacts with the charges in your body. The ions in your skin and tissue respond to the field. Positive ions, sodium, potassium, feel a force in the direction of the field. Negative ions, chloride and all the negative ions in your cells, feel a force in the opposite direction. These ions start to move just a little bit. They redistribute themselves. But here's the key thing. This redistribution of charge in your finger changes the field. Your finger doesn't just passively sit there in the field. It responds to the field, and that response alters the field everywhere. The field lines that were spreading out from the screen now connect to your finger. The electric field configuration has changed. And because the field has changed, the energy stored in the field has changed. And because the energy has changed, the capacitance has changed. This is what the phone detects. Think about this. The screen is measuring the capacitance maybe 100 times per second. That's why it can track your finger as you move it. Every few milliseconds, it's taking a new snapshot of the capacitance at every point on the grid. When the capacitance at one location starts to rise, then rises more, then reaches a peak, then starts to fall, the phone's processor can infer a finger moved across this region. It can calculate the trajectory. It can determine the speed. It can even tell how much of your finger is in contact, a light tap versus a firm press. Because more contact area means more capacitance change. But now you might ask, why does this work with a finger but not with a plastic stylus? Why can't you operate a touchscreen with a wooden pencil? The answer is conductivity. A plastic stylus is an insulator. The electric field from the screen doesn't induce any charge redistribution in plastic because there are no free charges to move. The field just passes through, essentially unchanged. A wooden pencil? Same thing. Wood is mostly an insulator. Even if there's a tiny bit of moisture in the wood, it's not enough to create the kind of capacitance change the phone is looking for. But a metal stylus works. You can buy special styluses for touchscreens, and they're always made of conductive material. The metal has free electrons, lots of them, and these electrons respond instantly to the electric field. The capacitance change is even larger than with a finger. The phone sees it clearly. And here's something fascinating. Why does the touchscreen work when you're wearing thin gloves, but not thick gloves? It's all about the distance. Remember, capacitance depends on the separation between conductors. A thin fabric glove might be 0.5 millimeter thick. The electric field can still reach through that small gap to your finger, and your finger can still affect the field enough to create a measurable capacitance change. But a thick winter glove, maybe 3 or 4 millimeters of insulating material, that's too far. The field is too weak by the time it reaches your skin, and the capacitance change is too small to detect. There's something else beautiful here, something that connects to deeper physics. The fact that your body is conductive, the fact that you can interact with electric fields, this is ultimately because you're made of atoms. And atoms are made of charged particles. Electrons and protons. The nucleus of every atom in your body is positively charged, and it's surrounded by a cloud of negatively charged electrons. As Feynman loved to point out, everything is made of atoms, little particles that are jiggling and wiggling all the time. And atoms are held together by electric forces. The electron is bound to the nucleus because opposite charges attract. When atoms join together to make molecules, they do it through electric interactions between their electrons. Chemistry is applied physics, biology is applied chemistry. And at the bottom of it all, it's electromagnetism. It's the electric force that holds matter together and makes the world work the way it does. Your body's ability to conduct electricity isn't some weird accident. It's a fundamental consequence of what you're made of. You're a collection of atoms, and atoms are electric. The ions in your body fluids, sodium, potassium, chloride, these are atoms that have lost or gained electrons. They're electrically charged. When an electric field appears, they respond. They must respond because they're charged, and that's what charged particles do in an electric field. Now let's talk about the electronics that make this all work. Inside your phone, behind the screen, there's a controller chip. This chip is sending out those AC signals to the ITO grid, and it's constantly measuring the capacitance. How does it measure capacitance? There are different techniques, but one common method uses the fact that capacitance affects how AC signals propagate. When you touch the screen and change the capacitance at a point, the AC signal at that point changes. Its amplitude might decrease or its phase might shift. The controller detects this change, and from the pattern of changes across the entire grid, it reconstructs the position and shape of your touch. The mathematics here is elegant. The controller is essentially solving an inverse problem. Given the measured changes in capacitance at thousands of points, what is the most likely distribution of conductive material above the screen? The answer is computed in milliseconds by specialized algorithms running on the phone's processor. The result is sent to the operating system, which interprets it as a touch event, a tap, a swipe, a pinch, and triggers the appropriate response in whatever app you're using. But here's what I want you to appreciate. The physics is doing the heavy lifting. Engineering is remarkable, yes. The fact that we can manufacture etho coatings that are uniform to a few nanometers, the fact that we can integrate 10,000 capacitance sensors into a piece of glass the size of your palm, the fact that we can measure picofarad changes in capacitance 100 times per second, all of that is impressive. But it's possible because the fundamental physics is there. Nature provides the electric force. Nature provides conductivity. Nature provides the behavior of capacitors. Engineers just had to be clever enough to use it. And think about the scale of what's happening. When you touch your screen, you're interacting with electric fields, and electric fields are made of photons, virtual photons constantly being created and destroyed, mediating the electromagnetic force between charged particles. This is quantum electrodynamics, QED, the theory that describes how light and matter interact at the deepest level. As Feynman showed in his Nobel Prize-winning work, every interaction between charged particles happens through the exchange of photons. When the electric field from your phone screen interacts with the charges in your finger, what's really happening is that virtual photons are being exchanged between the electrons in the ETO grid and the ions in your skin. These photons exist for only a fleeting instant, so brief that they can't be directly observed. But they're real in the sense that they carry energy and momentum and make things happen. This is the quantum mechanical reality underlying the simple act of touching your screen. You're not just making electrical contact, you're participating in a quantum field interaction. Billions upon billions of virtual photons are flickering in and out of existence in the space between your finger and the glass, carrying the electromagnetic force that lets the phone know you're there. Now, you might wonder, why go to all this complexity? Why not just use a simpler technology? Well, we used to. Older touchscreens used resistive technology. They had 2 layers of conductive material separated by tiny spaces. When you pressed on the screen, you'd push the top layer down until it made contact with the bottom layer, completing a circuit. The phone could measure where the contact occurred by sending currents through the layers and seeing where the resistance changed. Resistive screens were cheaper and worked with any object, your finger, a stylus, even a pen cap. But they had problems. They required actual pressure, so they felt less responsive. They weren't very accurate for multi-touch gestures, and they were fragile. The top layer would wear out over time from all that pressing. Capacitive touchscreens changed everything. They don't require pressure, just proximity. They're extremely accurate. They can detect multiple touches simultaneously, which is how pinch to zoom and other multi-touch gestures work. And they're durable because you're not mechanically deforming anything, you're just changing an electric field. But there's a cost. Capacitive screens only work with conductors. That's why you can't use them with regular gloves or a wooden stick. It's a trade-off. Engineering is always about trade-offs. Let me tell you something else that's remarkable. The ETO grid on your screen is constantly active, constantly generating those electric fields, even when you're not touching it. It has to be, because the phone needs to be ready to detect your touch instantly. There's no delay. The moment your finger approaches the screen, the capacitance starts to change and the controller sees it. This is why touchscreens feel so responsive. They're always watching, always waiting. And here's something that blows my mind. The energy involved is tiny. The electric fields on the screen are weak. The currents flowing through your finger are minuscule, microamps, maybe less. The total power consumed by the touch sensing system is a small fraction of a watt. Compare that to the power needed to light up the display, several watts, and you realize that the touch sensing is incredibly efficient. You're detecting the presence of a finger using less energy than it takes to light a single LED. This efficiency comes from the physics of capacitance. Capacitors store energy in the electric field, and when the field is weak, the energy is small. You don't need a strong field to detect a change in capacitance. You just need a sensitive measurement. And with modern electronics, we can measure incredibly small changes. We can detect capacitance changes of a fraction of a picofarad. That's a trillionth of a farad. It's almost nothing, but it's enough. Now let's zoom back out and think about what this means for the way we interact with technology. For most of human history, controlling a tool meant physically manipulating it, pushing, pulling, turning, striking. The tool responded to mechanical forces, but with touchscreens, we've entered a new era. The interaction is mediated by electric fields. It's contactless at the atomic level. You're controlling the device through an invisible influence that extends from your body. This is a profound change. It's part of a larger trend in technology, the shift from the mechanical to the electromagnetic, from the tangible to the quantum. Our modern world runs on electricity, on the flow of electrons, on the manipulation of fields, and we're getting better and better at it. The touchscreen is just one example. There are others. Sensors that detect magnetic fields antennas that receive radio waves, accelerometers that measure the motion of tiny masses. All of these technologies are based on electromagnetic phenomena, and all of them are rooted in the same fundamental physics that makes your touchscreen work. And the physics itself, it's not just some abstract theory that scientists argue about in journals. It's real. It's happening in your hand right now. The electric field is real. The capacitance is real. The flow of charge in your finger is real. This is the world as it actually is, not as we imagine it or as it appears to our senses. Our senses tell us we're touching glass. But the physics tells us something different. We're interacting with an electromagnetic field structure. We're perturbing the quantum vacuum. We're exchanging virtual photons. That's the reality. Feynman had a way of making you see this. He'd take something ordinary, a glass of water, a flame, a rainbow, and show you that if you really understood what was happening, it was more amazing, not less. The touchscreen is like that. On the surface, it seems simple. You touch, the phone responds. But when you understand what's really going on, the electric fields, the capacitance, the ions in your body, the quantum electrodynamics, it becomes a marvel. It becomes a window into the deep structure of reality. And here's the thing, this isn't rare or exotic physics. This is the same physics that's everywhere. The electric force that lets your touchscreen work is the same force that holds atoms together. It's the same force that makes chemistry work. It's the same force that lets your nerves transmit signals, that lets your muscles contract, that lets your heart beat. You're electrical. Your entire body runs on electricity, ion currents, voltage gradients across cell membranes, electric fields in your brain. The touchscreen works because you and the phone are both electromagnetic systems, and you're speaking the same language. There's a unity here that's beautiful. Everything connects. The quantum mechanics that describes electrons in atoms connects to the electromagnetism that describes electric fields, connects to the solid-state physics that describes semiconductors, connects to the circuit theory that describes capacitance. It's all one story. Nature isn't divided up into separate subjects like our textbooks are. It's one unified whole. And when you start to see the connections, the world becomes richer and more comprehensible. So the next time you pick up your phone and swipe through your photos or type a message, take a moment to think about what's happening. You're not just touching glass, you're reaching out with an electric aura, an invisible cloud of ionic charge that extends from your body, and the phone is sensing that aura through the capacitance it creates. You're communicating through the electromagnetic field. You're participating in a quantum mechanical interaction that involves virtual photons and the collective behavior of trillions of atoms. And the amazing thing, it just works. You don't have to think about the physics. You don't have to calculate capacitances or measure field strengths. You just touch and the phone responds and it feels natural. That's the genius of good technology. It hides the complexity. It makes the extraordinary seem ordinary. But now you know better. Now you know what's really going on. And maybe, just maybe, that makes the ordinary a little more extraordinary. Maybe it makes you see your phone not as a disposable gadget, but as a sophisticated instrument that bridges the macroscopic world of your finger and the quantum world of electrons and fields. Maybe it makes you appreciate the incredible journey that took us from Maxwell's equations in the 1860s to quantum electrodynamics in the 1940s to the smartphone in your pocket today. Because that's what science does. It takes the world apart and shows you how it works. And when you see how it works, really see it, deeply understand it, the world becomes not less magical, but more magical. Because reality, it turns out, is far stranger and more wonderful than any story we could make up. Your touchscreen is a miracle. Not a religious miracle, but a scientific miracle. A triumph of human understanding and ingenuity built on the foundation of physical law. And every time you use it, you're touching the quantum universe. You're interacting with the electromagnetic field. You're part of the most fundamental processes in nature. That's what Feynman would want you to see. Not just the convenience of the technology, but the deep beauty of the physics underneath. The universe is understandable. Matter obeys laws. And when we understand those laws, we can do remarkable things. We can build devices that respond to the touch of a finger through the subtle rearrangement of electric fields. We can make glass come alive with light and interaction. We can turn invisible quantum phenomena into everyday tools. And that's not magic. That's something better. That's physics.